All right, guys, so we left off in class talking about molar mass and conversions between moles and grams. So we're going to take moles to the next kind of natural place, which is called a mole ratio. So far we've used moles to change between the number of individual particles to the number of moles. So using Avogadro's number. We've also used moles to go from between grams and moles, so we can actually measure grams in a lab, so we can then convert them to moles using molar mass. So now we're going to look at mole ratios. So anytime we talk about a ratio is a comparison of values. So when we compare any two values, we're creating a ratio. A mole ratio is a comparison of the moles of one thing to the moles of another. So in our case, the moles of one chemical to the moles of another. We can write ratios, mole ratios, any sort of ratios in a lot of different ways. So we're going to see a couple of the different ways, maybe how we'll state them and how we can actually write them down. So we're going to use the chemical Fe2O3 iron 3 oxide. Is the name of that chemical for some of these examples, for these first few examples. So when we look at that chemical formula, what it represents, it says for every 2 iron atoms, there are blank oxygen atoms. Well, based on the chemical formula, Fe2 means there's 2 iron, and for every 2 iron, we have 3 oxygen atoms. So it's a ratio of the atoms in iron oxide, right? It's a 2-to-3 ratio of those atoms. We can also write the ratio. It says what the ratio of oxygen to iron. So there are 3 oxygen for every 2 iron. So that's our ratio of oxygen to iron. We can also write them with that like colon in the middle. So you might see it written that way. Now we want to not just look at individual atoms though, because individual atoms are microscopic. We can't see them with our eyes. They're too tiny to deal with. We're never just going to use one molecule of a chemical. We're going to use a whole lot more. So if we instead had a mole of this chemical, so if we had 1 mole of Fe2O3, then the ratio of our atoms stays the same. Okay, so for every 2 moles of iron, there are 3 moles of oxygen, right? So it works if we're comparing the number of atoms, but the ratio stays the same if we're comparing the number of moles of that chemical. So it just depends on what label we're using for it. So another way we can write ratios, so we can kind of state the ratio for every, how number of this, we have this many of the other thing, right? We can put it in this colon form right here, but we can also write them as fractions, which is probably the way we're going to see them the most. So if we were to fill in these ratios, we would just use those little subscript and move them to the front. So for every 2 moles of iron, we have 3 moles of oxygen, or we could write it the other way. For every 3 moles of oxygen, we have 2 moles of iron. And you may notice that the way they're set up, we could actually set up some conversions with those and change between things. So we'll look at that in a little bit. Okay. So this is a visual representation of what's going on there, right? If I had a pile of iron oxide, and this is actually what it looks like. Iron oxide is what you might know better as rust, right? When iron rusts and reacts with oxygen, it forms iron oxide. That nice rust color, as we call it. Now, if we were to zoom into that, we would see that if we had one of those particles, we'd see that there are 2 iron atoms, or orange ones. The iron is what makes it orange, for every 3 oxygen atoms. So if I had a mole of this chemical, then I have 2 moles of iron and 3 moles of oxygen. Okay, it's going to translate into moles, those numbers of each element. All right, so what that means also is that since a mole is 602 hexillion things, our iron would be 2 times that amount. would be our number of total iron atoms, and our total number of oxygen atoms would be 3 times that amount. That's a ton of atoms, right? So it's so much easier to count in moles than it is to count in individual numbers of atoms. All right, so let's try another one. We can also use mole ratios when we are dealing with larger chemicals, when we have more than 2 elements. The same things apply. We can create ratios between any of those parts of that chemical. So if we looked at this, for every blank carbon atoms, there are blank oxygen atoms. Pause for a second and see if you can fill that in. All right, so hopefully we got for every 6 carbon atoms, there are 22 oxygen atoms. And again, we're just getting them from the subscripts in that chemical formula. And I believe that one is glucose. That's what's in our bodies, glucose. And then the next one says the ratio of oxygen to hydrogen. So we'd want to put oxygen's number in first. Its subscript is 11. Hydrogen is 22. So they have an 11 to 22 ratio. All right. All right. The next one says if we had a mole of this chemical, the ratio of atoms stays the same, right? Same thing as our last one. So for every 6 moles of carbon, there are blank moles of hydrogen, so it should be 22, and blank moles of oxygen, so it would be 11. So for every 6 moles of carbon, there are 22 moles of hydrogen and 11 moles of oxygen. Right? It's just using those subscripts to create a ratio. Oops. So we can create ratios between any 2 of these chemicals and write them as fractions as well. So take a second, pause, and fill in those top 3 ratios and then unpause. All right, hopefully you were able to work through these. So oxygen would be 11, carbon would be 6, so that's an 11 to 6 ratio. Carbon is 6 and hydrogen is 22, so it's a 6 to 22 ratio. And oxygen is 11, hydrogen is 22, so that's an 11 to 22 ratio. Some of these you could also reduce, like we could reduce this to a 1 to 2 ratio. That's fine as well. All right, now the bottom part is looking at 1 mole of the whole chemical and comparing that to just one of the elements. So we can also not just go between moles of one element to another, but from 1 mole of the whole chemical to an individual element. So when we look, it says 1 mole of C6H22O11 has 11 moles of hydrogen. Or excuse me, oops, I did the wrong thing. Not 11. 11 on the mind. Hydrogen has 22 moles of hydrogen. Same thing over here. If we had 1 mole of that chemical, for every 1 mole of that whole thing, there are 6 carbons, 6 moles of carbon. All right, so we can form lots of different ratios. Now, what do we do with them? Well, we can do some calculations with them. So it says, why are mole ratios useful? They allow us to convert from information about one chemical in a formula to another chemical, so one element to another. They also allow us to convert from the whole chemical to an individual element, or the reverse, go from an individual element to the whole chemical. All right, so it says how many moles of oxygen. So now we really want to pay attention to not just the unit it's talking about, moles, but also the chemical it's talking about, right? So how many moles of oxygen are there in 4.6 moles of that whole chemical formula? So same one we had on the previous slide. So as we've done on other questions, we're going to go ahead and write our given amount first. All right, and set up our railroad tracks. We're going to go ahead, just like the other ones, copy those units and chemical to the bottom. This is where it becomes really important that we write our chemical as well, because we are going to change chemicals. Right? What it's asking us to find, what we circled there, is moles of just oxygen. We're just going to put O. Oops. just O. So how do we set up this number? Whenever you're dealing with looking at the entire chemical, if it gives you that entire chemical there, we're going to go ahead and put the 1 there, right? We're breaking down from the entire chemical just to one element. So in 1 mole of that chemical, there are 11 moles of oxygen. And we can tell by that little subscript 11 next to the oxygen. So what we need to do here to solve, 4.6 moles times 11 on the top, we're going to divide by 1. So 4.6 times 11, and I get 50.6. Now we've only got 2 sig figs there, so we do have to round this to 51. And we get moles of oxygen. All right. So if I had 4.6 moles of this chemical, within that I have 51 moles of just oxygen. Okay. All right, let's try another one. If a sample of that same glucose molecule has 4.78 moles of carbon, how many moles of hydrogen are in the sample? So now we're switching between moles of carbon and moles of hydrogen. Okay, so we're talking about this chemical as a reference, but we're really switching between carbon and hydrogen. Okay, so we're going to write down our given 4.78. And it says just moles of C. So again, we want to pay attention to what it gives us, what it's talking about. So we're going to copy that unit down to the bottom, moles of C. It asks for how many moles of hydrogen. Put moles of H. So we want the comparison, the ratio between those based on this given chemical formula. So in that chemical formula, there are 22 hydrogen and 6 carbon. So 22 to 6 is our ratio. So we're going to take 4.78, multiply by 22, and then we are going to divide by 6. Oops. Divide by 6. And we get, I got 17.52667. Bunch of numbers, right? Again, our original value here, we have 3 significant figures, so our answer gets 3. So we get 17 point, that 5 is going to stay the same because the next digit is a 2. And we cross out our moles of carbon, we're left with moles of hydrogen. Right? So if we have this sample, we know how much carbon there is. We want to know what the amount of hydrogen would be based on that chemical, based on that glucose molecule. Okay. Hopefully we're doing pretty good. Last slide. So, a couple more to try here. How many moles of oxygen are there in 0.58 moles of KMnO4? Potassium permanganate, my favorite. So, we're looking for moles of oxygen. It gives us moles of potassium permanganate. Write down our given amount. Ooh, getting messy looking. All right, we're going to bring down our unit, moles of KMnO4. And it asks for just moles of O, oxygen. So again, when we have that whole chemical, when we're trying to go from the whole chemical down to just one element, we're going to say in one of that chemical, there are, in this case, 4 oxygen. Okay? In one of those formulas, there are 4 oxygen. So in 1 mole of that chemical, there are 4 moles of oxygen. All right. Same process. Multiply, divide, 0.58 times 4. I get 2.32. Again, our given amount has 2 significant figures. So we get 2.3 moles of oxygen. All right, last one. This one has 2 parts to it. So if a sample of MgSO4, no, that's just written weird. Sulfate is 2 minus. Yeah, that doesn't actually need parentheses. That's spazzy. Okay. If a sample of MgSO4 has 9.5 moles of sulfur, how many moles of oxygen are in the sample? So we're comparing the amount of sulfur that we're given to the amount of oxygen in that chemical. Write down our given. We want to go from moles of sulfur. We copy down that unit in chemical. It wants moles of oxygen. So we're going to compare. There's 1 S in the formula to 4 oxygens in that formula. So we need to multiply by 4. 9.5 times 4 gives us 38. And that's 2 sig figs. And we got 2 sig figs. We are good. Moles of sulfur cancel. We get moles of oxygen. Now the second part says how many moles of magnesium, right? So we want to do another problem. We're going to do a separate problem for that one. So again, we have 9.5 moles of sulfur. And we want moles of magnesium. Now this one's actually pretty straightforward. We can see in our formula that we have 1 sulfur and 1 magnesium. It's a 1-to-1 ratio, so our number doesn't actually change. But our chemical does. Okay, so sometimes that happens where we end up with the same amount. And so it's a 1-to-1 ratio, and we get the same number. All right. So using our chemical formula, we can change between individual elements, or we can change between an element and the formula itself, okay? So we've got a lot of options there. Your homework is the mole ratio practice, and actually, let me see if I can add, do it on my other computer. Oh, yeah, I can do it. New prompt. I need to be able to write on here really quick. There we go. All right. So on here it says mole ratio practice. Go back. And the so we've got our video here. So finish your Pear Deck. Use the video to finish Pear Deck. Okay, got your mole ratio practice, and then there is the AP Chem letter. It's posted on Teams, and it has a place for you to fill out the form and sign. Okay, I need you guys to read through that. It has to do with what's going on at the end of the semester, or not the end, but during the semester in terms of the AP exam, and where we're going to get to, and what we're going to cover, and what you need to do in terms of preparing for your AP exam and stuff. Okay, so it's really important that you read through that letter and sign it. Okay. Have a great day, guys, and I will see you in the next class. Thanks.